All right, so function composition today. Function composition is an operation on functions. And the notation for function composition is a little circle there. It's not the letter O. It's not fog. It's function composition. And you read that F composed with G of X. That's how that's read. F composed with G of X. The way it works is you take the F of X function and you plug in the G of X function into it. So that's the workings of it. Is you take whatever function is listed second, take it and plug it into the first function that's listed. And you can find the composition function, excuse me, the composition function out of that. And then we can find domain of those things because they're functions. We know about domain for that. And we can also kind of think about things here. What's G of X besides a function? What's it short for?
Pardon the interruption, but a reminder, seniors, the Heart of the Champion Scholarship application is due in guidance right now. If you have that completed and have not submitted it, you need to bring it to the guidance office at this time.
Right. All right. So somebody said Y. That's right. It's the Y values for the G of X function. So the G of X function, these are Y values. Well, that was convenient. So Y values from G of X plugged in the place of X in F of X is kind of what's going on. So when we get into practice in the textbook, they'll actually have you doing some function composition with numbers involved, and so you've got to think about that an X value plugs into the G of X function first. We get the Y value that comes from it. Plug that Y value in the place of X in the F of X function. We're going to look at it in a more generic sense in notes here and find composition functions, and we'll talk a little bit about the other part as we go. So let's first describe domain. Set of all X values in the domain of G of X, and we're using G of X in terms of it's the second function such that G of X just got started are in the domain of F of X, or the first function. So basically what it does is it takes the range of the second function and makes it, and you look at it as far as the it being the domain of the first function listed out of that. A lot of words right there, and it's kind of a twisty little definition there, but in the actual work of it, it's not that bad. So let's state the domain of each function and the composite function. Then find the composite function. That's going to be our instructions for this. A few problems here. We're stating the domain of each function individually, and then we're going to state the domain of the composite function, and then we're going to find that composite function. We're going to do the actual function composition with this. So get two functions here. F of X is equal to 2x squared minus 3 and g of x is equal to something pretty easy, 4x out of that. So let's take the domain of f of x, and then the domain of g of x, and then we'll kind of do the last two parts together a little bit here. All right, so domain. What are the red flags that we look for when we're trying to find domain of a function just in general? X is in the denominator, or that makes it not a polynomial. Negative exponents will put x's in the denominator. What's the other red flag? There are only two. Square roots with x inside. Okay, those are things that create red flags when we're finding domain. All right, so we look at function f of x. Does it have any of those red flags? No. So what's its domain? All real numbers, negative infinity to positive infinity. We look at g of x. Does it have any of those red flags? No. So its domain is from negative infinity to positive infinity. Since there are no restrictions on either of those, the domain of f composed with g of x would be from negative infinity to positive infinity, since there are no restrictions on that. If there are restrictions, we'll get to that. You know, what happens when there's restrictions on the first function? What happens if there are restrictions on the second function? All right. So let's find the function or the composite function. F composed with g of x means take g of x and put it in the place of x in f of x. So we're going to take 2 parentheses 4x squared minus 3. So we took g of x and we replaced x with it. That's all we're doing to find a composite function. And then we're going to simplify. What happens when you square 4x? 16x squared. We'll multiply that by 2 next. That'd be 32x squared minus 3. There's our composite function. F composed of g of x. Pretty easy one to start off with. Nothing really too fancy about that. Notice that our composite function, we don't see any red flags in it either. That's important because the domain was negative infinity to positive infinity. All right. Example B. All right, so we didn't have any restrictions on example A. So let's make sure example B does. Okay. Again, we're going to follow the same instructions. We're going to state the domain of f of x, state the domain of g of x, and then state the domain of our composite function, and then actually find the composite function. So a lot of stuff going on with this one because we see on both of these, we got x's in the denominator. So there's going to be restrictions on both of those pieces. So let's get the domains of each of those individual functions first. How do we find the domain of f of x? 5 equals 0. So x cannot be negative 5. So there's our, and I'm just going to shorthand it here because the end result we're looking for is the domain of the composite function. That's the main part of the game here. Let's find the domain of g of x. G of x has x minus 1 in the denominator, so we say x minus 1 equals 0. x can't be 1. Now, here's where the restrictions start making things a little tougher as far as the composite functions domain. If there are no restrictions on either of those pieces, then there can't be any restrictions on the composite function. If there are restrictions on the individual functions, then there's got to be some sort of restriction on the composite function. Now, here's what we've got to know is when we're plugging in g of x, if we're trying to find f composed with g, that's our composite function that we're looking for, then we're taking g of x and putting it in the place of x in f of x. If we're replacing x in f of x, what's the only thing that x can't be? -5. So what we need to know then is when does g of x equal -5? When is that function we're putting in the place of x equal to the x that it can't, that said it couldn't be? So if there's a restriction on the first function listed in the composite statement, then you've got to find out when is the second function equal to that restriction. Okay, so we're going to set up that equation. G of x is equal to -5. So g of x is 4 over x minus 1. Set that equal to -5. And solve it. How do we solve that? Like proportions, yeah, I could multiply by x minus 1 on each side, or cross multiply, whichever way you want to say it. So that's going to be 4 is equal to -5x plus 5. Subtract 5. -1 is equal to -5x. Divided by -5. One-fifth. So on the domain of the composite function, f composed with g of x, on that domain, we get two different restrictions. We get the restriction on g of x. It's automatic because that's the first x that we're using, right? Because the way the composite function is, it's the second function listed in the composite statement. Has the x's first, and then you get answers from those and put those into that. So the restrictions on the domain of this one, x can equal 1, and then the restriction that comes from the first one isn't -5, because that's not going to be an x value that we're going to use. We're going to use the y values from g of x. So the restriction comes from this work that we did. That's the 1/5. This is set notation. We're going to write it in interval notation as well. So interval notation would be from -infinity to 1/5, union 1/5 to 1, union 1 to infinity. Be able to go both of those directions. All right, now define the actual composition function, or the composite function. So we're taking g of x and putting it into the place of x in the f of x function. So that's going to require us to do some fraction work. We got 1 over, instead of x, we're going to put 4 over x minus 1. And we can't leave a fraction inside of a fraction, right? So we got to do a little bit of work here. So in order to add 4 over x minus 1 and 5, what do we have to have? Common denominator. What would be the common denominator for that particular problem? X minus 1 would be the common denominator. So 4 over x minus 1 all this is still under 1, plus 5 times x minus 1 over x minus 1. Pretty easy fix there because the denominator is 1, so you just multiply top and bottom by the piece that needs. So we're going to simplify that a little bit. 4 plus 5x minus 5 over x minus 1. Now we still got a fraction inside of a fraction, but that fraction can be simplified a little bit further. 4 and negative 5 come together to be 5x minus 1. All that's still underneath 1, so heavy fraction bar there. And then x minus 1. Dividing by a fraction is the same as doing what? Multiplying by its reciprocal. And then that gives us our composite function finally. F composed with g of x. 1 times x minus 1 is x minus 1. 1 times 5x minus 1 is 5x minus 1. And there we have our composite function. Now, if we just found the composite function and then found the domain, we would find that the only restriction would be the 1/5. We would lose that restriction of the x not equaling 1 because we didn't find the individual domains. This is why we need to find the individual domains first, okay? Because if you just do the composite function, you may have some of the restrictions, but you may not have all of them. Sometimes you do have all of them, but we know that if we're finding the domain of this, then we set the denominator equal to 0, and we find that x can't be 1/5. We had that in our domain, but we missed the part about the 1 not being part of that. So that restriction doesn't show up in the composite function. So you've got to be diligent to do the domains of each individual problem before you're going to the composite function only. Common mistake in this section is that you just do the composite function and not the rest of it. So here, let's do another set. F of x is x plus 3, or under square root. G of x is something nice and linear, 2x plus 5. We're going to find g composed, or f composed with g of x and the domains. That's your instructions. Find the domains and the composite function. That's what our instructions were. So domain, we got to find domain of f of x. So how do we find domain of f of x? Nope. It's in the square root. What kind of numbers can we take the square root of? Can it not get weird? Not just square numbers. We can take the square root of 8. We can take the square root of 1. We can take the square root of 2. Take the square root of 0. What kind of numbers can we not take the square root of without it getting weird? Negatives. So set x plus 3 greater than or equal to 0. Solve that. So x got to be greater than or equal to negative 3. Then let's find the domain of g of x. They're nice to us on this one. G of x was a nice linear function. Are there any restrictions on g of x? None. Okay. But because there were restrictions on f of x on the first function, remember we're taking g of x because of the composite function statement was f composed with g. We're taking this g of x stuff and putting it in the place of x there. So we're taking all of this stuff and making it fit underneath the square root. So that's where we've got to match up to get our composite domain. We've got to say, okay, when does this meet these restrictions? When does the second function meet the first function's restrictions? So that's the question we got to answer to get our domain of our composite function. When is g of x greater than or equal to -3? So we set that up, 2x plus 5 greater than or equal to -3, and solve. Divided by 2. It happens when, it works when x is greater than or equal to -4. So the domain of our composite function, so domain of f composed with g, is all x's as long as x is greater than or equal to -4. Even though there were no restrictions on g of x, we had restrictions on f of x, so that caused there to be restrictions on the composite function. Okay. So now let's find f composed with g. We're going to take and actually do the math and plug that in. So we're going to have square root. Instead of x, we're going to have 2x plus 5 plus 3. And we're just going to simplify that. And there we have our composite function. Nothing else you could do to that to make it better. Now on this one, if we had found the composite function and set that greater than or equal to 0, we'd have got the same answer as our domain here. We wouldn't have missed anything. But it was because we didn't have any restrictions on the second function listed. Sometimes it works, sometimes it doesn't. But doing it this other, the longer way works every time. So that's my advice, is do it the right way every time. So, restrictions on the first one are going to mean restrictions on the composite function. Restrictions on the second one are going to mean restrictions on the composite function. Restrictions on both are going to be restrictions on the composite function. No restrictions on either, no restrictions on the composite. Okay, so you can take that. I guess that's the only shortcut, is that if there are no restrictions on either function, then there's none on the composite function. Then you don't have to do much. So let's take the same two functions and let's do a different composite function and see how it changes the problem. Let's find g composed with f of x and the domain. So different order on the composite function here. Not f composed with g, but g composed with f. So paying attention to which way the composite function is listed makes a difference. So g of x, same problem as we had in example C. The restrictions on g of x are none. They don't have any because it's just a linear function. No red flags, so that's negative infinity to positive infinity. But f of x, the domain of that one, again, we're setting x plus 3 greater than or equal to 0. You got x has got to be greater than or equal to -3. Now here's the difference with this one and the last couple that we've done. The first function listed in my composite function doesn't have any restrictions. So these restrictions are going to get us the y values we need. And we don't have to find out when is f of x equal. We don't have any restrictions to set it equal to or set it greater than or equal to or anything like that. There are no restrictions on this. So all of these x values are the only things that are restricting the function. So there's a restriction right here. We don't have any restrictions to check on here. So we don't have to do that step. So our domain of our composite function, g composed with f of x, the only restrictions are going to be that x is got to be greater than or equal to -3. And then to find that composite function, g composed with f of x, we take the f of x function and put it into the g of x function. So the f of x function was square root of x plus 3. And this one's nice and beautiful. You don't have to do anything. Nothing you can do to simplify that. Stop prepping. So the composite function picks up the restrictions from the second function in the composite statement, and then wherever that second function is equal to the restrictions of the first function. This time we didn't have any restrictions on the first function, so we just had those as that. Okay. Interval notation for that would be from -3 to infinity. Didn't write the interval notation there. In a hurry. You're able to bounce back and forth between those two. All right, let's do a tougher one here. H of x is equal to x squared minus 5x plus 7. And then k of x is 3x over x minus 2. Excuse me. Okay, so we're going to find h composed with k of x and the domain. So first thing we want to do is get the domain of each of the individual functions. Are there any restrictions to h of x? No x's in the denominator, no square roots. That's a parabola. We know it's a quadratic. We know it has a domain negative infinity, positive infinity. That's going to help us out because anytime the first function listed in the composite statement doesn't have any restrictions, then that means I don't have to worry about setting up an equation and solving it. That's the shortcut. That's nice when that happens. Okay? Step 2, domain of k of x. How do we find that? Set the bottom equal to 0. Stuff we know, x minus 2 equals 0. X can't be positive 2. Quick and easy solve, but that's the restriction we have. Because we don't have any restrictions on h of x, the first function listed in our composite statement, then we don't have to set up an equation that says when does k of x equal that restriction. Well, k of x is going to get, it doesn't matter because this is no restriction out of it. So the domain of our composite function is just going to match this. Of h composed with k of x. And all x's, as long as x does not equal 2. And then negative infinity to 2, union 2 to infinity. There's our domain of our composite function. Now the fun part, actually finding the composite function. So we're taking k of x, put it in everywhere there's an x, into the h of x function. So h composed with k of x. So that's going to be 3x over x minus 2 squared minus 5 times 3x over x minus 2 plus 7. Okay, we want to simplify that. So that's going to be 9x squared over x minus 2 squared minus 15x over x minus 2 plus 7 over 1. I wrote that as a fraction for what reason? Because what's it doing with three fractions there? Putting them together. We want to write this as one fraction. We want to write this like one of our functions in the last chapter of the rational functions, okay, which is one fraction. So we need to find a common denominator. First fraction has x minus 2 squared. This one has x minus 2. So the common denominator is going to have an x minus 2 and another x minus 2. That 1 over there is not going to really do anything to the common denominator. So our common denominator is going to be x minus 2 squared. And that's the main reason I did not multiply this part out down here. I want to leave that in fraction or in factored form. Okay. So the first fraction I don't have to do anything to. It's already got the right denominator. But the second fraction, I need to multiply it by x minus 2 on top and bottom. So that's going to give me negative 15x squared plus 30x over x minus 2 squared. The third fraction, it only has a 1 in the denominator, so it needs the x minus 2 squared on top and bottom. So x minus 2 squared will be x squared minus 4x plus 4. And then I'm multiplying that times 7. That's going to be 7x squared minus 28x plus 28. So that's what's going to be on top, plus. I'm going to write this like this so I don't screw up the sign. And then that'd be 7x squared minus 28x plus 28 over x minus 2 squared. Simplifying that, put your like terms together. 9x squared minus and negative 15x squared would be negative 6x squared. And then plus 7 would be positive 1x squared. 30x and negative 28x would be plus 2x. And then plus 28. H composed with K of X. So adding and subtracting rational expressions. Common denominator. Doesn't happen on every problem. Just make sure we did one in notes here so that got practice doing that. Okay. Technically, we should try to factor this numerator, but there's nothing that multiplies to be 28 that adds to be positive 2, so there's nothing that can cancel and simplify. You always got to look to do that, but this one doesn't simplify, so we leave it alone like that. We can see in our composite function here that x minus 2 is the only thing in the denominator that would give us that restriction of x can't be 2, which we already had for the domain of that. When you're doing this, if it just asks for the domain of that, you don't have to find the composite function to find the domain. You find it without it. It may be helpful sometimes to find that composite function, but it's not a requirement. In order to find the domain, you don't have to do that. Let's take the same two functions, for example, f, and flip it around. H of x is equal to x squared minus 5x plus 7. And then k of x is equal to 3x over x minus 2. And we're going to find k composed with h of x and the domain. We're going to turn it around here. This makes it a different problem and a different set of circumstances. So we're going to find the domain of k of x, or and then the domain of h of x. Domain of k of x, we know we're setting x minus 2 equals 0. X cannot be 2. H of x, there were no restrictions because it's a quadratic. Linears, quadratics, cubics, those polynomial things don't have any restrictions on them. So now the difference in this one and the previous example is the fact that the first function listed in the composite statement or composition statement has restrictions. So we need to know when is the second function that we're plugging into it, when is it equal to 2. So when is h of x equal to 2? We're setting up x squared minus 5x plus 7 equals 2. That's anytime the first function in the composition statement has restrictions, you've got to do this work. Or maybe better said, that's the only time you have to do this work. Okay, so we're setting up that quadratic equation. How do we solve that? Subtract 2, get it equal to 0. That opens up using factoring if possible. Is there anything that multiplies to be 5 and has to be negative 5? No. So can I solve this? How? Quadratic formula. Is negative b plus or minus b squared minus 4ac divided by 2. So that's a negative 5. All right, so we end up with 5 squared, which is 25, minus 20. That's the square root of 5. Are those real solutions or complex? Real. So that means they are the restrictions on the domain. If they were complex, then they wouldn't create restrictions on the domain. Remember, complex doesn't restrict the domain. Real solutions do. So these are real solutions. So the restrictions on our domain are of the composite function. So domain of k composed with h, or x does not equal those things. 5 plus or minus the square root of 5 over 2. Interval notation for that. 5 minus square root of 5 over 2 is going to be the smaller one. So that'd be negative infinity to 5 minus the square root of 5 over 2. Union 5 minus the square root of 5 over 2 to 5 plus the square root of 5 over 2. Union, I can give myself enough room to write like a kindergartner here. 5 plus the square root of 5 over 2 to infinity. There's the domain. But again, same idea. If the first function listed in the composite or composition statement has restrictions, then you got to find out when does the second function equal that. That's what we found here. When does the second function equal the restrictions of the first function? Now let's actually find the composition function, the composite function. So h composed with k of x. So we're taking k of x, which was the fraction, and plugging it in, or excuse me, or taking the k composed with h. That's what we're doing, not h composed with k is what we did last time. K composed with h. That's what we're doing. So we're taking the quadratic and plugging it into the fraction, which is a lot easier than the other one was. 3 parentheses x squared minus 5x plus 7 over x squared minus 5x plus 7 plus, or excuse me, minus 2 is the denominator. Simplify that a little bit. Not a hard step. 3x squared minus 15x plus 21 over x squared minus 5x plus 5. And we know that that doesn't factor, so we know that that is not going to simplify. A lot easier on that one because you only had one fraction to deal with. Not much work. This numerator doesn't factor either, other than the 3 coming out, which doesn't help any. Okay. All right, get your textbook out real quick, and we'll look at a couple of problems that, like what I'm trying to. Oh, I'm going to do a formal example with them, but I just want to look at them real quick. So turn to 6-1, page 40. 404, page 404. And look at number 7. Okay. Number 7 gives you a table with x values and then 2 different y values, f of x and g of x. Okay. Over on the right, it asks you to find these composite function values, not composite functions, but function values. On a part, it gives you 1 in the parentheses there. What is that? It's an x value. So I go to 1 on the table in the x row. And then f composed with g, I need to find the g of x answer first. What's the answer for g of x when x is 1? 0. Then I take that, and that's my new x to go into the f of x function with. So in the f of x function, I go to 0 on the x row and get the y value in the f of x row, which would be -1. Okay. All right. Let me write it out. Page 404, number 7. It gives you an x row. You get -3, -2, -1, 0, 1, 2, 2, 3. And then you got an f of x row, and it gives you the y values of f of x, -7, -5, -3, -1, 3, 5, 7. F of x must have been linear. And then g of x, 8, 3, 0, -1, 0, 3, 8. G of x must have been an even function by looking at those y values. All right, so they give you that. A part says find f composed with g of 1. What that means is you take g of 1 and plug it in to the f of x function. So we need to find first what's g of 1. So we go to 1 on the x row, and the g answer is 0. And then that means we're going to find what's f of 0. So we go to 0, and the f of x answer is -1. Yeah, you trace it through the ordered pairs is what you're trying to do there. B part, what's it ask for? It asks for f composed with g of negative 1. So what's the first thing that I need to find? Negative 1 on the x row. So I'm finding g of negative 1 first, which would be 0. And then the next thing I'm finding is f of 0, which is negative 1 again. Okay. Find a different one here. Let's do C part. C is a good one. C asks us to go G composed with F, so it turns it around, of negative 1. So the first thing that I'm going to find, first function value would be F of negative 1. So I'll go up here to my rows, and we know F of negative 1 is negative 3. And then go into the G of X function with negative 3. That gets us 8. We're tracing through. Always start with the second function listed. Use that x value that they give you. Get the answer to that. Use that as the next x value. Okay, let's go ahead and do D part. See if we can follow this one. G composed with F of 0. So we're going to go up here to our table, and the x value we're looking for is 0. So we find 0. It's right here, and it's G composed with F. So which one do we go into first? F. So G composed with F, F of 0 is equal to 1 or negative 1? Negative 1. And then that negative 1 is now the new x value. And we find that, here it is, and go into G of X. G of negative 1 equals 0. So that means the function is equal to 0. Or the composite function is equal to 0. Let's try E. We're going to do this whole problem. E is G composed with G. What the what? And so can't really screw this one up on the first step. We're going to find G of negative 2. So I'm going to go up here to my chart, and X is negative 2. G of negative 2 would be 3. And then I'm taking that and making my new X with that. The final answer should be 8. F composed with F of negative 1. Sounds like we're working with your grades. Never mind. F composed with F. So negative 1 is my x value. I'm going to the f of x function first. So negative 1 goes to negative 3. That's my new x value. So I go up here to negative 3, and the y value goes into f. It's negative 7. We're tracing it through with the ordered pairs. That's what you're doing. Okay. So practice for section 6.1, page 404, 7 through 44, 67 through 70. We skip a little section in there. We'll do something with that later on. Got 20 minutes left in class today, work day tomorrow, quiz on Wednesday. Folks that missed the test Friday, you need to get with me about making that up. very, very soon.